Is it okay to have both? Yeah. Okay. So maybe I can start with the question first. Is anyone here using, so who's developing an MPI? Who knows what MPI is? More, that's good, that's good. Are you using Intel MPI or using MVAP? I guess MVAP is just the other one that's available on the machines. Do you know? Do you know which one is mostly MVAP? I mean, is there any interest in me going over the Intel MPI slides? Or should I just skip over those and just sort of focus on the tracing stuff?
Who's interested in Intel MPI?
A few? Okay. Well, I have a few slides at the beginning. You guys are more than welcome to tell me to skip something if you feel like you're not interested in it. So, first thing to note is this says Cluster Edition 2015, which is the latest officially available. But 2016, which is the next major version, comes out next week. I do have a slide on 2016, but the main functionality, which what I'll mostly be talking about today, is really valid both for any version of the tool that you download. So we have 3 different editions. The one that I'll mostly be talking about, so we have Composer Edition, which includes our C++ and Fortran compilers, as well as our performance libraries, so anything like the math kernel library, the integrated performance primitives, any of our sort of threading interfaces, things like threading building blocks or Silk Plus. So those are all included in the Composer Edition. On top of that, you can add analysis tools for the node level. So Gary Carlton would have talked to you about vTune. So vTune gets added into what we call the Professional Edition, as well as a couple of other tools. They're really focused on memory and thread checking on the node level, as well as if you are trying to parallelize your application, we have an advisor tool that covers both threading and vectorization. And then the Cluster Edition includes all of those plus our MPI tools. So that includes the Intel MPI library and then the trace lines and collector, which is our sort of multi-node, multi-process profiler. So that's sort of the high-level overview. I guess you guys have Cluster Edition locally, so you should have access to all of the tools. So 2016 comes out next week. Just a quick preview of what it'll include. So it'll have the new Vectorization Advisor. So it's a brand new tool. Do people know what vectorization is? Yes, okay, good. So it's a brand new tool that helps you look at pretty much your hot loops. So which are the loops that you spend the most amount of time in? And then are those vectorized efficiently? So we take some information from the compiler reports. We take some information from doing memory mappings in order to figure out what the unit strides are when you're doing the memory accesses. And all of that is sort of bundled into this nice interface. So what it'll do is it'll tell you if something is vectorized or not. It'll also tell if it's not vectorized, why it's not vectorized, right? So you might have a data dependency in your loop that might be causing the compiler to not do the auto-vectorization. And then it'll tell you potentially also how to solve it, right? So we'll give you a lot of samples about what the particular issue is and then how to potentially resolve it, as well as also an efficiency rating or performance gain rating. So how much potential performance you can gain by fixing whatever vectorization issues you might have. So that's brand new in 2016. So as part of the beta, we just finished a long multi-month beta, and it'll be part of 2016 as well. We also have, and I'll talk about this a little bit more, is we have this new scalable MPI profiler tool. So I'll be talking today about the trace lines and collector, which collects a lot of really great information, but there's a lot of it. So when you're doing large scale scaling, so anything, above 10,000 cores, 30,000 cores, 100,000 cores, right? So anything, when you do something like that, you'll care less about the details, but more about where your potential bottlenecks might be, right? So you need to try and identify what those key metrics will be in order to do optimizations at the high core counts. So we sort of introduced this tool that's very lightweight that allows you to do that. And then, is there any big data research, data analytics stuff going on here? Not really. So we have a brand new, so similar if anyone here has used the math kernel library, which is a set of math and engineering routines that are very highly optimized for Intel architecture. So they basically just go down to the assembly level and they code a lot of those optimizations. So this is the same idea, except it's all about data analytics algorithms. And those are all available as part of 2016. And then we have a bunch of improvements in terms of the compiler support. So latest OpenMP standard is supported, latest MPI standard is supported, latest language binding, so what is it, C, C++, and Fortran. So Fortran 2015, I guess, would be the latest. Is it mostly, yeah, oi. Is there mostly C or C++ or Fortran development here? Mostly C? C? C++? Any Fortran at all? Okay, that's good. Awesome. So I'm going to then start off talking a little bit about MPI, or Intel MPI specifically. So we're based on mpitune. Well, actually, the latest version is based on mpitune 3. So we're have a really close collaboration with the team at Argonne. We share, so our mpitune is open source project, so we take a lot of that source and compile it and optimize it for Intel architecture. On top of that, we actually add a lot of optimizations if you're running on an Intel processor. So we detect whatever processor, whatever architecture you might be running, and then we have specific algorithms that might be defaults versus if you're running on something else, or any other x86 architecture, I guess. We also do really close collaborations with a lot of the fabrics providers out there. So on your cluster, very likely you have InfiniBand. It's InfiniBand. So what we will do is it will sort of select the fastest fabric available on the machine without you having to specify anything, anything on the command line. We also support the new Intel TrueScale Interconnect, which I don't know if you guys have that. It's not available here, but that's also supported out of the box. And mostly what we've been focusing in the past few releases has been scalability. Intel is doing a big push in getting their tools to scale out to high core counts. So if you have, so the latest run we did was 262,000 MPI processes. We did that on the Supermach cluster over in Germany. And it was, I mean, it's like out of the box. So we had to set some environment settings, but mostly the library was able to scale out without any special recompilations or changes within the source code and so forth. Now, how many of you actually have applications that scale to 262,000 MPI ranks? One person, 2 people, excellent. So even if you don't scale that high, a lot of the optimizations really tend to focus on things like memory efficiency and using the resources as best as we can without much additional overhead from the MPI side for the actual MPI communication. And all of those tend to trickle down to the lower core counts anyway, right? So a lot of our defaults tend to be pretty good even at the lower scales as well. So I have a couple of performance slides. I like showing them because then you can kind of compare how we do against some of the other MPI implementations out there. But at the same time, it's all about how you have it set in your environment. So what I generally recommend people to do is you have the library available, just go ahead and run it on your machine with your application, and then tell us what the performance is like, right? So this is all out-of-the-box numbers. So we haven't optimized any of these libraries. So we have Intel MPI 5. So this is the previous version, which is 5.0. Platform MPI is probably one of our bigger commercial competitors. And then we have MVAPage and then OpenMPI. So the open source ones, all we've really done is, so we sort of compiled the source code as we grabbed it from the website. We didn't really do any optimizations on it. But that's also true for our library, and that's also true for Platform MPI, right? So on your machine, I imagine MVAPage is probably going to be optimized specific to whatever architecture, fabric, and so forth you have running. I guess the beauty of Intel MPI is that we ship pre-built binaries, so you don't have to worry about compiling the latest version of MVAPage available specific for your machine, right? So you don't have to mess with configuration files, make files, and so forth. We just provide a libmpi.so. All you really have to do is just link with it and then run with it. So everything here is normalized to OpenMPI, which is the 1. And then other stuff is then speed up or slow down according to that absolute or to that relative value. So you can see that we tend to do, out of the box, we tend to do pretty well. 16 kilobytes is about, so on the x-axis is messages, so how big your message is, and the y-axis is the speed up. So our sweet spot tends to be about 16 kilobytes. And that's mostly just because some of our thresholds, or some of our default thresholds tend to be set at about 16 kilobytes, but those can easily be changed. So this is running a set of Intel MPI, so this is running a set of MPI kernel tests that does anything from just ping pong to running through all of the collective operations, so broadcast, all reduce, and so forth. So it's sort of a combination of all of those performance values. So this is running 192 processes over 8 nodes. So by default, as I mentioned, we tend to pick the fastest fabric available across the node and use that when running. Now, if you go to the next slide, now we're scaled out to 1,536 processes, and that's spread over 64 nodes. Now, you can see that we tend to do really well, especially at the higher core counts at that 16 kilobyte value. But again, so if let's say you send a lot of, really tiny, small 4-byte messages, right, you can easily change those thresholds and then figure out how that behaves or how the library behaves in your in that particular environment. And then this is Windows, yeah. Is there any Xeon Phi development happening? Do people know what Xeon Phi is? Yeah, there's a couple, okay. So Intel MPI has supported Xeon Phi for, since its inception, so it got released maybe 2 or 3 years ago, and we have a new version of the sort of mic architecture coming out soon, and it'll support, so Intel MPI will support that as well. Okay, so the first thing I want to mention is you can, because we ship pre-built binaries, you can pretty much install Intel MPI at any level of your cluster. So what I tend to do a lot is I run on a machine that I'm not an administrator for, so I'm just a regular user. So it has some version of Intel MPI, most likely the latest one available, installed under, let's say, /op/Intel. If I want to test a different version, I can easily install that package under my home directory and then switch between the two as I'm running my jobs. So it's pretty much just running a set of scripts in your environment. Do you support modules here? Yeah, so it'd be similar as just loading a different module for whatever version of Intel MPI you have available. Now, anything that I'm about to talk about, pretty much any threshold values, changing the settings for how large your, what kind of algorithms you're using for, let's say, your broadcast, how big your message buffers might be. So all of those are customizable at runtime. So there's a huge set of environment variable settings that you can select and pick. And that's how you can sort of tune and optimize the library. There's no need to recompile or relink. Actually, a lot of our libraries tend to be compatible between versions as well. So if, let's say, you have an older version of Intel MPI, you can easily test with the new runtimes without having to rebuild your executable. So this is how you build an application. I guess it's pretty standard. So we provide a set of compiler wrappers. We don't provide our own compilers because there's really no need for that, right? So we tend to use whatever's available in the system. So if you use MPI ICC or MPI I4, so the extra I stands for Intel. So if you use those wrappers, we would tend to try and figure out if you have the Intel compilers available on your machine. And if you do, we'll select those. If you do things like MPI CC or MPI F77 or F90, then we would try and look for the GNU compilers as they're available in the system. We also provide a binding kit. So if you're using like PGI compilers or AppSoft or anything else, then we provide binding kits for those as well. So one thing to keep in mind is because we don't provide our own compilers, we sort of rely on what's available in the system. Just because you're using, let's say, MPI CC, you could overwrite an environment variable value or have a runtime flag and actually use the Intel MPI compiler. So sort of keep that in mind when you're running. Mostly we just tend to look at what's available in path and LD library path in order to pick what compiler we use. And this is how you run. So we provide an MPI run command script that works really well if you're running some sort of batch scheduler. So I don't know what you guys do here. Is it LSF of some sort or PBS? Oh, it's Torque. OK. So we fully support all of the major ones, including Torque. And mostly, I guess what that really means is you don't really have to specify a host list. We do that interaction for you through the MPI run command. So we actually interact with Torque, grab the host list, and then we run on whatever Torque tells us is available as number of nodes. Now, one thing to note is we have, if you run Intel MPI by default, we'll do sort of this group round robin idea. So we would use up all cores available on the current machine first before we go to the next one. So that means that, so in my example here, I'm running 2 ranks on my local host, but it's very likely that I have more than 2 cores available on my local machine. So that means that both ranks are then run on node 1. Now, you can easily overwrite that just by setting a runtime option that -per host switch. What that really helps is if you're doing hybrid programming, so if you have MPI plus OpenMP or any other sort of threading. So in that case, you probably don't want to fill up all of your cores with MPI ranks. You probably want to do maybe 1 MPI rank per socket or even 1 MPI rank per node, and then have the rest of the cores be available for your OpenMP threads. So in that case, you can easily just do -per host 2 here, and that means that you put 2 MPI ranks on the current node, and then the next 2 will be put on the second node, and so forth. So it just goes down the line. And I guess it also picks individual sockets too. So if you want to do 1 MPI rank per socket, that's done automatically for you. You can also do some tricks. So if you want to run 2 different executables, or if you want to be very specific about how many ranks on which hosts and so forth, so those are easily changed by providing a bunch of so what we're calling argument sets, right? So you can individually provide the number of ranks, which node or which host you're running on, and then which executable you want to run on. Or you can sort of combine all of that. So if this gets very complicated, you can actually combine everything into a configuration file and do that. Any questions so far? Is that very different than how you run MPI applications? Is it somewhat similar? Or do you do something now that you're wondering how to do with Intel MPI maybe? Nope. Okay. So one other thing about the library is it gathers its own statistics. So as it's running, it actually tries and figure out how many messages you're sending, who are you sending those messages to. If it's a collective, then who's involved in that collective? Are you creating a new communicator? So by default, it's not going to print anything out, right? So by default, it's just going to collect these statistics. But you can enable for it to print everything out to just a regular text file by setting the MPI stats environment variable. So the higher the value, then the more details will be made available to you in the final text output. It really only goes up to 10, so 10 would be the highest. And then you can also, but you can specify the scope. So if, let's say, you just want to keep track of your collectives, then you can just say your scope is just my collectives, or you can specify, certain ranks that you want to record information for, and so forth. So so you can see here the type of information, or why it might be helpful too. So it's so for example, for each process in my job, so this is process 0 from total of 16, it tells me who, so I'm the source, then who am I communicating with, and then where is the majority of my transfers, right? So where am I transferring a whole bunch of information to? It also provides me information about my collectives, right? So if, let's say, I know I'm doing a bunch of collectives, but the one that's really using up the majority of my time is this all reduce here, because I'm calling it 216 times in my application. So most likely that's a potential performance bottleneck. So if I want to optimize anything, that's probably what I want to take a look at first. It also gives you, so each collective actually has its own set of algorithms. So for example, for I think all reduce, I think we have 5 different algorithms that you can select. And some of them might be topology aware, some of them might not be. And they're all described in the reference manual. So one thing you can do, so we try and sort of pick the best defaults. So one thing you can do is figure out what default is being set here, right? So I'm using algorithm 6. And it's accounting for about 7% of my total runtime. I can play around with that algorithm selection and then figure out if something else would work better for my particular topology. I talked a little bit about fabric selection, but so what we do is we try and pick the so when we do communication between ranks, if the ranks are all local to the current node, we'll always use the shared memory device, just because that's always going to be the fastest. If we want to do communication remotely to other nodes, then we're going to try and pick whatever fast fabric is available on the machine. So by default, this will be set to the DAPL value, which is this guy right here. Now, if something goes wrong, so if you don't set MPI fabrics, which is the environment variable to change the fabric selection, by default what will happen is if something goes wrong with when loading the DAPL drivers, it's actually going to fall back to regular Ethernet sockets, right? So it's just going to use TCP. And in that case, if you're not seeing the performance you're expecting, it's very likely because it's just running over Ethernet. In that case, you can enable debug, MPI debug. So if you set it to pretty much any value, 2, 3, or higher, it'll print out exactly what fabric it's using at the beginning. One thing, so I don't know if you have the Open Fabrics available on the machine, if that's the software stack you're running, OFED. I might also recommend running with OFA, with the OFA setting. That's not our default, but we've gotten some nice performance results on it if you're running, especially if you're running the Open Fabric software. Okay, and then there's a lot, so if you look at the manual, the reference manual, there's probably 110 pages, probably more, of environment variables and how you can select all of them. what we recommend you do instead is, unless you specifically know what you need to change, then you can easily change that. But if you're really not sure, if you're not really getting the performance you really need, we provide an automatic tuning utility that will do a lot of that for you. So this is how you run it. So there's sort of two modes, right? So there's the cluster tuning mode, which you just say MPI tune. What this will do is it'll run a set of benchmarks on your cluster. It'll try and figure out things like what kind of processor you're running, what kind of fabric you have available, how big the messages, or how much memory I have available per core, things like that. And based on those settings specific to your hardware, it will try and figure out the best Intel MPI environment variable settings. It'll save all of that into a single configuration file. So you do that once. And then you can reuse, so you can apply that configuration file to any Intel MPI job that's running on the machine. And it kind of works the same way if you do application level tuning. But in that case, you do MPI tune -application, and then you provide your command line here. So what this will do is instead of taking a look at your hardware or your cluster environment, it's actually going to take a look at what kind of messages am I sending back and forth, what kind of MPI calls am I making, and it'll really focus the tuning just for that specific subset. Okay, I do have a couple slides on hybrid just because I think Steve mentioned you guys are doing a lot of that. So this is specific to Intel MPI and hybrid, but I imagine you probably already have some settings that you're using with MVAPage. So Intel MPI supports pretty much all of the available threading models out there. So anything from stuff that's already available for you by linking with a third-party library. So if you use MKL, a lot of the MKL routines are already threaded. Or if you're using OpenMP, or even down to pthreads, right? Or any other threading library you have available. Now, what we do is, so the first thing we recommend is you have to link with the thread safe. If you do have a hybrid code, you have to link with the thread safe version of Intel MPI, just because it ensures that there won't be any sort of migration of the threads across ranks and so forth. So we've seen a lot of issues where people just use the regular sort of non-thread safe version of the library. They're using it with either a MKL routine or maybe something else that's multi-threaded, and they start to see issues. So if you have the latest version of the library available, this is actually default. So the multi-threaded version or the thread-safe version of the library is actually default. So as long as you link with libMPI, that should be taken care of. There's really and some people worry about performance hits, but there's really nothing. So the reason why we made it default is because the performance of the thread-safe library is about the same as, it's actually pretty much the same as just the regular non-thread safe. So this is what we do. If you're doing some sort of a threading, then we assign something called a domain for each rank in your job. So let's say you have a 2-socket system and you're running 1 MPI rank per socket. So that means the domain of each rank will be the size of that socket, so 6 cores or whatever is available. In that case, we guarantee that the threads, the OpenMP threads that you're running, won't really leave the specified domain for the MPI rank. Now, we can really control the affinity for the threads themselves, right? So the only thing we really have control over is the MPI ranks. So if you want to do affinity for the threads themselves, then you have to do KMP affinity or any of the other OMP settings. But those are easily specified on the command line. So this is just an example. So so this is a mixed environment. So you're running both on my Xeon and my mic, the Xeon Phi machine. Then I probably want my domain to be slightly smaller on my host. But then I want to increase the domain. So I have a lot more cores available in Xeon Phi, so I want to increase the size of my domain on my cards. You can easily specify, so you can do a -env and specify any of these settings here. So OMP num threads and KMP affinity, you can easily specify that on the MPI run command line. and those will be applied directly to the MPI job. Do you guys have any questions, or do you run in a specific way? And maybe I can just give you suggestions about how to do it with Intel MPI. So that's sort of the idea behind it. We generally try and do a pretty good job of respecting, so we recognize, somewhat we recognize if you have OpenMP threads or any sort of threads running, and we try to do as good of a job as possible sort of in controlling those threads. And there's a lot of customization you can do. What we tend to do is, so if you set OMP num threads, then your domain will be automatically calculated for you. So it's just the number of cores divided by the number of threads you have running. Okay. I guess I have a couple more things, but one of the last ones is, I did mention you can change the algorithms for each of the collectives. So if you're doing a lot of, so if you figure out from gathering statistics that you're doing a lot of all reduce, then we have 7 different algorithms available for this all reduce. So we try and pick some default, but really at the end, it sort of depends on your environment. It depends a little bit about, it depends a little bit on the messages and what kind of work you want to do within that MPI job. So what you can do is you can either do the automatic tuning. So that automatic tuning will do we'll run through all the collectives for you as well. But if you don't want to, but the automatic tuning could also potentially take some amount of time. So if you don't want to do that, what you can do is just start a whole bunch of jobs, just changing the all reduce algorithm, and then figure out if you get any performance benefit out of it or not. Okay. This is 5.1, and also be updating this for, this is 5.0, but also soon we'll be updating this for 5.1, which is our latest version. And mostly what we really, as I mentioned, mostly what we really try to do is, so we support the latest MPI 3 standard. Is there anyone here doing development with MPI 3? So the new standard includes things like non-blocking collectives, or if you want to send really large messages, so anything that's over 2 gigabytes, it supports that. Or if you're looking to do a bunch of one-sided communication, so the one-sided implementation in MPI 3 is significantly better than the one in MPI 2. So we've added support for that as well. And then mostly we've really been focusing on scalability and memory efficiency in the latest versions. Okay. So that was actually it on the MPI side. Any questions? No. Okay. Yeah.
A small question, I guess. If you're using a higher level language, which is not on the list, but you're calling routines that use through interface with routines that are C++ or C. Mm-hmm. Can you still use your thing, and can you use it without creating another isolated package for running the lower level routine? Oh,
sure, yeah. So your question is if you're running, let's say, Java, Julia, and you actually have Julia wrappers for C++ routines, you can definitely use Intel MPI underneath for your C code, yeah. So you're running Julia? So I work with Arch Robinson, who is a big proponent of Julia, yeah. Okay. So in that case, I'll move on to the tracing profiling part. So we have a tool called the Trace Analyzer Collector. So back in the day, there was a company called Palace in Germany, and they developed this tool called Vampire Trace. And Vampire Trace, so the company itself was actually purchased out by Intel quite a few years ago. And so that application developed into the Trace Analyzer Collector. There is also a Vampire Trace today, which is still being developed by ZIH, I think, one of the other universities in Germany, which is slightly different, but the two tools sort of had the same beginnings. So the idea behind the trace lines and collector is it's taking a look at your MPI applications, and it's trying to gather as much information about each MPI event that's happening as it can, right? So it's as the application is running for each process, anytime you make an MPI call or you exit an MPI call, you send a message, you receive a message, whether the message is part of a point-to-point or a collective operation. All of that data is being recorded. Now, when it's done collection, so when it's done recording all this information, then you can do the analysis after the fact. So all of the analysis is done post-mortem. The collection, so because it records so much information, you can get quite a bit of data, right? So I guess I've seen trace files or profile runs where they recorded, several megabytes up to, a couple of gigabytes of data. And it really depends on how much MPI communication you're doing, how many ranks you're running, and so forth. But the tool, but it records all of this information, so it's not really statistical based, right? It doesn't just care about gathering statistical information for you. It records so much information is because it gives you this nice overview of your entire application run. So from the start of your MPI job to the end of your MPI job, for each rank, you see exactly what's going on. It's fairly lightweight up to a certain level, right? So it has its restrictions. But I think on average we see no more than 3 to 5% overhead for your total runtime. It's really meant to be run on production codes. So if you do have any optimizations, if you're doing any of the optimization flags for the Intel compiler, those are all fully supported as well. So this is more or less how it works. So if you take a look at, starting from source code all the way to creating your application, creating output, then you can insert the trace lines and collector in a certain places. Probably the one, or I guess the other thing I should mention is that there's two main components to the tool. There's the collector part, and then there's also the analysis part. So I'm going to talk about them slightly separately. So the collector is just a library. So you link or you load that library as you would MPI, for example. So the fastest, or probably the easiest way to do it is to just enable runtime switch for Intel MPI. So it's just, if you just call -trace on your MPI run command line, it'll start. The trace collector library will be dynamically loaded. What it'll actually do is it'll start intercepting all of your MPI calls and then start recording data for each call you're making. Now, you can do the same thing at the linker stage. So if you want to create an executable that's already been instrumented, then you can easily just do -trace on the linker line. And they'll create a brand new executable that already has the collector library linked with it. Now, the trace collector by default will really only record information about your MPI calls, right? Honestly, initially, we don't care about anything else, right? The tool is really meant to give you a high-level overview of what your MPI communication looks like. Now, you can, if you want to, recompile your entire application. So there's a special switch that's part of the Intel compilers, and that's called -tcollect. So if you do -tcollect and you recompile your code, this will give you information about all routines in your application, not just the MPI bits. Now, this will, of course, collect a lot more data, so be somewhat careful with the information, with enabling that switch. Now, we also provide a set of rich APIs, so if you really want to be specific about where you start the collection, where you end the collection, then you can do sort of a VT trace on and VT trace off. So it's fairly easy to use the API calls and start collection and end collection at any given point. So as the application is running, it actually the collector creates individual trace files for each process, so for each MPI rank you have in your job. So what it'll do is it'll record information about all the MPI calls, all the MPI communications, And then when it's done, so when you make that MPI finalize call at the end, it'll create sort of this main STF or structured trace file. So we do this separately so that we can be fairly scalable when you're doing the analysis later on, right? So let's say you gather enough data for 2 gigabytes, right? You never want to load that much data into memory because it's probably going to take forever and you might even crash the system. So instead what we do is that the final trace file, the STF file here, is actually a very small percentage of the total data collected. So when you're loading it, you're only going to be loading, let's say, 20 megabytes into memory, and then you'll be running that. So you're going to be seeing sort of this high-level overview. And as you're zooming in or you're manipulating the data you're seeing, then you're only pulling in individual pieces from the rest of the collected data. And then when you do the analysis, you can do it with the trace analyzer. So the reason why I'm talking about them separately is because I tend to do analysis. So I have access to a large machine that's in New Mexico, and I'm based in Illinois, right? So for me to run some sort of an X environment on that cluster and then have to do analysis remotely is a little painful. So what I tend to do a lot is I do my collection. So I submit a batch job, I do my collection on that large machine, and then I transfer all of the trace data locally to my Windows machine. So the cluster I'm running on is Linux, locally on my Windows machine, and then I do the analysis locally. So that's what Steve was talking about earlier when he said if you want to run just the GUI component, just the analysis part, you can do that on your local system. I think I talked a little bit about this, but the reason why we do event-based tracing instead of just gathering statistical data, which is what tools like gprof do, is it really helps you determine if you have any temporal dependencies in your code. And you'll see an example of that in a little bit, right? So if you have one process that's holding everyone else back, that's going to become really obvious on this timeline view, but you won't be able to figure that out if you're just looking at statistical data. So this is how, just an example how you run it. So it's just MPI run dash trace. Number of ranks, everything else in the command line stays the same. Now, if you want to run this within Vapage, then there's a special library you just have to link with. And I can give those details to you if you want after this. So dash trace is actually implemented from the Intel MPI side. It's not something that the trace collector really has control over. So if you're running it with different MPI library, you just have to manually link with those, with the collector libraries. That's really it. And then when it's done, you just do trace analyzer, which brings up the GUI locally. You can either just call trace analyzer and through the menu navigate down to whatever trace files are, or you can provide an argument here, and it'll open up that trace file immediately. I think I went through the majority of this. So this is what it looks like, sort of in high-level overview. So this is doing, it's actually doing a comparison between two different runs. So I have one run. The blue sections are time spent in computation, so pretty much anything that's not MPI. And then the red sections are time spent in MPI. So you can see here, while everyone sort of starts the MPI segment at about the same time, they don't finish at the same time. There's actually a serial execution that's being forced within this MPI application, which is generally not what you want to see, right? So you want to see well-balanced, well-parallelized, somewhat application. What the little lines are that go across, or I guess I should say all the little horizontal, vertical lines. All the little vertical lines are actually processes. So this is the data for each individual process. So you can see exactly if, let's say, rank 6 is then communicating with all of its neighbors by these little lines that go across it. So each line would designate an individual message that's being sent between the different MPI ranks. And at the bottom, so this is sort of the event data on top, And then at the bottom, because we have all this information, it's really easy to extract the statistical data out of it. So you can see, total time spent in MPI designated by red, and then how much time you're spending doing actual work or computation. So I think I'll actually do a demo at this point. Do you guys have any questions? Okay. So let's see if I can do this. I'm sorry? So I have, oh, there's no code. I'm just going to run the GUI. So I have run this application previously on the Linux machine on some small cluster that I have available to me. So I've done, so you guys can see it here. So I've done about 16 ranks. It's running a Poisson solver, which is one of the sample codes that we ship with the tool. So you can do this yourself if you want, or you can run this with your own application. So what this will do is, so I've already collected the trace data one time, and now what I'm doing is I'm doing the analysis locally on my machine. So I have, I can open a new trace file, or I've done this demo before, so I can also open up one of the existing trace files, but I'm just going to open up a new one, and I'm going to go up a level. So we're going to take a look at doing Poisson with single send receives. So the way that this algorithm is implemented, so Poisson does nearest neighbor communication. So it's an iterative implementation of the algorithm. So each data point, I guess, sends its data to its nearest neighbors, and then they all do exchanges. So you can kind of see this when we look at the timeline. Now, the first thing you're going to see is you have a bunch of blue, right? That's my computational time, and then I have a bunch of red, so that's my MPI communication time. So MPI is not so bad, right? So at first glance, it actually doesn't look horrible, so this might be okay. But now what we're going to do is we're going to take a look at the event timeline, which is the first, probably the timeline that I use the most, just because it gives that nice overview. So on the x-axis, you're going to see it's just the time spent in your application from second 0 to whatever. I mean, this whole thing didn't take more than, I think, a couple of seconds, so it's pretty short. And then on the y-axis, it's the MPI ranks, right? So you can see each individual one, process 0 all the way to process, well, it says 14, but there's 16 ranks. So I can scroll up and down. Now, there's a bunch of initialization at the beginning. I don't really care about that, so I'm just going to skip it. So what I'm going to do is I'm going to click and drag, and it's going to zoom in into a particular section of my trace data, right? So it automatically refreshes, and I don't know if you noticed, but it also refreshed the statistical data at the bottom as well. And that's because if I want to zoom in on a particular segment, I don't really care about what the rest of the application is doing. I want to really focus on the stuff that I'm looking at immediately. So you can kind of see the iterations. So there's about one here. There's another one here, right? So it just keeps going. So what I'm going to do is I'm going to try and zoom in just on one particular two. Maybe let's do 3, right, at this point. So you can see, so it becomes kind of obvious, right? So all of them start work at about the same time, and they all start their MPI communication at about the same time, but everyone exits out dependent on each other, right? So it seems like the last process is waiting on its nearest neighbor, which is the previous process to finish, who's waiting on its previous neighbor to finish, and so forth, right? So there's this sort of stair-step pattern that you generally don't want to see if your application is somewhat well-balanced. Then they enter another computational phase, which for everyone takes about the same amount of time, but you are already offset. So at that point, due to your first MPI communication, you've already lost whatever advantage you might have had, right? And so when you hit the final barrier or the final synchronization point, which is actually, this is not a barrier, but it's a MPI all reduce, I think. So it's doing the final computation. Then it's actually a reverse pattern, right? Because the first process will spend the least amount of time waiting in that first MPI segment, then it's going to spend the most amount of time waiting in that final synchronization point. Now I can get more information just by doing right-clicking. So I can do ungroup. Whoops, sorry. I can't see very well. Ungroup MPI, there we go. So I can ungroup the MPI. So I had previously colored this, and I had saved the current state. But initially, you'll just see just the shades of red. But the important part is you see you're doing some send-receive stuff here, and then another set of send-receives here, and then you're doing the all reduce at the end, right? So if you want to really figure out where in your code this is happening, you can do that. You can actually, so I haven't enabled this, but you can actually get, so if you click on details here, you can actually enable source code references. So this will add another column to this window, and you can click a button and it'll take you directly to a source code. So it's just a runtime switch. I can tell you what it is if you're interested. And the other thing to note is you can actually see all the information for that's being collected more or less, right? So for this all reduce, I know who initiated it, right? Or which process that I clicked on, right? So it's P4, how long it took, and the exact start and end times. I can do the same. So if I hit one of those little lines, I don't know if that's actually. Okay, there we go. So if I hit the little lines, what's actually going to give me is all this information about my all reduce. So you're going to see that, you know, for the all reduce call, it involved all MPI ranks that I have available. So it's running MPI COM world. And then for each one individually, you can see how many bytes each rank sent, and then when it started, how long the duration was, and so forth. And if you had different communicators, you know, this would also be shown here. So this is an example of the type of information that the tool collects as it's running. Now the event timeline, as I mentioned, is probably the one that I use mostly. There's also a few stuff at the bottom. So we're looking at just the application and then send, receive, and an all reduce, which is basically what the routines up here are shown, right? Now I can also, so the application code is also grouped, so I can ungroup it. But that's actually not going to help me any, right? Because all I did was the runtime instrumentation of this. And so what that will give me is just the MPI calls. So everything else is sort of grouped into this user code. Now I do have a trace of this recompiled with tcollect, and I'll show you in a little bit how that information is different. There's another chart that I wanted to show you, which is the quantitative timeline. So this one, the x-axis is still the runtime of the application, or whatever time segment that I'm looking at right now. But the y-axis, instead of doing each individual rank, it's actually telling you how many total ranks are executing a given piece of code at the same time. So this is really, especially if you get to a higher number of ranks, this becomes pretty useful so that you can notice some of these stair-step patterns immediately, right? So you can see in this particular example, you can see exactly where this sort of delay or latency gets introduced in your MPI application. I can also do load balancing, which I guess in our case it's pretty obvious, right? So you can see that you have process 0 spending almost no time in the send receive, while at the same time you have process 14 spending, probably 4 or 5 times as much in the send receive. So you can sort of get a quick view. Just make this a little bit bigger. You can sort of get a quick view of whether your communication generally is balanced or not. So let me actually, so there's a call tree and a call graph, but let me open up the other trace file, because it's a little bit interesting. So right now the call tree is not very exciting, just because it's pretty flat. So it's just a single application. It just has main, and it calls a bunch of stuff. But mostly all you're going to see. So if I reset the zoom here, there it is. Then you're going to see just user code, and then I'm calling a whole bunch of MPI calls, right? Now, yeah?
Process 0 at the beginning is just white.
The process 0 at the beginning is just, it's just white. That means that it hasn't called anything. So it's probably sitting idle until something happened. So it wasn't using the CPU, or it wasn't making any sort of, it hadn't entered the MPI init phase, more or less.
It seems to me that some of the colored red is actually should be white as well, because it's waiting for.
So that's a good point, right? So your point is, should some of the red segments actually be white? So that's actually not the case, right? So white just means that it's not doing anything MPI related. So this tool gets loaded when you make the MPI init call, and then it stops recording when you make the MPI finalize call. So it records sort of everything between. So basically what this means is it's probably doing some system level setup. So process 0 is probably doing some system level setup before starting up with, before calling the MPI init call. Now, so your question brings up a different point, though. So in all of the red segments, that includes time spent in physically executing that MPI call, plus any idle time spent in that MPI call. And we don't want to remove the idle time, because that's really where you're introducing that extra latency in your code, right? So you want to be made aware if you are idling in an MPI call, so that you can change it, right? So you can maybe rearrange your algorithm, so you can maybe post some of your receives a little bit early, so that when you do, let's say, a non-blocking send, you can post some of your sends a little bit early, and maybe do some non-blocking communication in order to remove some of that overhead. But yeah, so the red sections would include physically copying the MPI message from one process's memory to another process's memory, plus any idle time spinning. So let me show you the one that I recompiled with -tcollect, just so you guys can see what the difference is. So I'm just going to open this up. So it's the same application. The only thing that's different is, instead of just running with -trace, I just recompiled with -tcollect. So now I'm seeing the same view. So let's open up the event timeline. And take a look at that. So now when I do ungroup application, so now all of a sudden it actually gives it to me on a source file level, right? So these are a bunch of Fortran 90 source files. That's what the application is using. So you can see each one then. So if I ungroup each one individually, then it'll give me the actual routine that I'm using, right? So in this case, it's a red-black, right? So the routine is called Poisson red-black. So I can either do this individually for each one of these, which will waste a lot of time. Instead, what I'm going to do is I'm going to bring up the aggregation, the function aggregation window. And what I'm going to do is, so right now, it's telling me that it's showing some routines that are grouped, right? So stuff with the G here means that it's grouped. My MPI stuff is also grouped, and then other stuff that's not grouped, right? Because I just ungrouped it. So instead, what I want to do, instead of this sort of half group, half ungrouped stuff, I'm just going to select all functions. So this is available for you by default. There's nothing extra you have to do. If you just hit all functions and then hit OK, that's going to ungroup everything in your code, so you're getting down to the actual individual routine levels. So now you can see let's sort it really quickly. Whoops. So now I can see sort of where, so as part of my computational phase, I'm spending a lot of time in this red-black calculation. But then here's my all reduce that we saw earlier. So now when I zoom in on a particular segment, then you can see exactly what the sort of the execution pattern is too. So you can see exactly what's happening. So now, so let me go up a level actually. So now when I hit this call tree, it's a little bit more exciting, as exciting as looking at source code can be. So you can see that I'm calling my main, then I'm doing some error handling at the beginning or setting up some of my error handlers, and then I'm starting my execution, right? So I get my communicator, and then I start doing red-black exchanges. So why that's helpful is the call tree gives you sort of this high-level overview of pretty much this is the call stack, right? What is happening in your code as it's being executed. Now, the nice thing about it is I know right away that this red-black routine is where I'm spending the majority of my time in. So what I can do is I can see, well, in red-black, it seems like I'm calling a couple of functions, and then I'm doing the send, receive, and all reduce. So if I want to do any optimizations, then I know I really should focus on optimizing this particular set of data, right? Because that's where I'm spending the most amount of my time in. So that's sort of the idea behind having the call tree available. One other thing I wanted to show you is that comparison view. So this is just the originals. So this is implemented using, let me close this down. So this is implemented using blocking communication, which is really where that communication bottleneck is coming from. So if you change the code and you actually implement it using non-blocking send receives, then the communication pattern will change. So I've actually done 2 runs, one with blocking, one with not blocking. So what I'm going to do here is I'm actually going to do compare of the blocking one, which is the one that I have open, with the non-blocking one, which is this one. So I'm going to hit OK. And what that's going to give me is sort of this view between, so what it's going to actually do is it's going to try and do the 2 timescales at about the same. So you can see that one is much shorter than the other over in terms of the runtime. And some of the information it'll give you is, so for example, in my all reduce, I actually had almost 4 times reduction in my all reduce time between the 2 runs, when doing non-blocking communication versus blocking communication. So it'll change some of the charts to give you ratios versus just the absolute numbers. Do you guys have questions? Yeah.
Is it possible to have the call tree that the code is not, let's say it's not run synchronously, and different processors can see how they,
Yeah, so what I was showing you, is this the right one? Yeah, so what I was showing you was all processes. You can also do children of all processes. And then you can actually do it per process. So it's process 0, and then process 1. So you can see exactly what each process is doing. It's not really well, I guess one thing you can do when you do it side by side is open up the call tree again, which is that flat profile. Sorry, where is it? Function profile. So you can see okay. There it is. So you can do children of all processes. Yeah, I don't know if there's a way to do side by side. You could open it up in two views, so two instances of the same trace file and sort of do it side by side that way. Yep. But if you do all children, if you do children, then it'll give you for each individual rank what is the call tree, because it might be different, right? So. Yeah. Yeah, so I don't have that enabled here, but if, for example, you're looking at a specific call, let's say this one right here, so if you do details, oh, I guess I do have it enabled, but I don't have the source code, which actually doesn't help us any. But so you can actually click this button, and it tells me now the source code is available. But if you did have available on the machine, what this will do is it'll bring up the source code immediately. Yeah. So the way to enable that, so it's not enabled by default, but the way to enable that is just to set an environment variable before you run.
Does the code need to be executed normally, or these files to be generated, or can it be used in case of an exception?
Can it be normal? Is that what you said?
Let's say if that code crashes.
Oh, if the code crashes, right. So the issue with when the code crashes is it's never going to get to that MPI finalize, right? So in that case, you might, so if your application is well behaved, it's probably going to call MPI abort at that point. So we have, if you know your code is crashing, so the default library can't really handle that. But if you know your code is crashing, we provide a fail-safe version of the library that you can link with initially. And then it'll collect the traces up until the point of crash, or up until that MPI abort is called, and then you'll be able to sort of finalize the trace even if it is crashing at the end. That also helps if, let's say, you do a SIG interrupt on your machine. So if you do a Control-C, which usually calls SIGINT on any modern OS. This is off. So if you do a Control-C on any modern OS, you can just link with the fail-safe version of the library, and then kill your application at some point midway, and then it'll also do the collection up until that point as well.
Reverse clock helps too.
It what?
Reverse clock helps too.
Right.
No, I'm serious. What you do is you have something that counts for clocks.
Mm-hmm.
And then you go to 1 minus that, 2 minus that, 3 minus that, and it's like a reverse clock.
Oh.
It's exactly what you're.
Exactly. Okay. Is this something that you mean on the application level? You've done that?
I mean, you wouldn't necessarily be counting, actual computer clocks. You're counting something.
Okay. Right.
And you can go backwards.
Right. Exactly. Yeah. So I did have a few more slides, but let me skip through some of these since we already went over them. There is a few other functionalities in the tool that I wanted to mention really quickly. So the first one is, so we have something called the Ideal Interconnect Simulator that's part of the GUI. So this is all post-processing stuff, right? So this is, you've already collected the data and you're trying to manipulate the data in order to figure out if there's something in your application that can perform better and so forth. So what this will do is it'll take a look, so it'll run through your entire application run, and it'll figure out how your code will behave under ideal conditions. So that means 0 latency and infinite bandwidth. So sending a message happens instantaneously. So in this case, what's going to happen is any sort of potential bottlenecks that are left over in your code will be will really be something that's dependent on the way that you've implemented the algorithm you're running, right? Something about the MPI communication and how you've implemented that. It also means that your application is probably communication bound, right? So a faster interconnect will help you to get better performance. So this is how it's more or less done. So if you look at two different examples, right? So in the first example, I'm posting a non-blocking send early, and then continuing my communication, computation, and then the receive is posted at some point after. And then in the second case, I'm actually posting my receive early, and then I'm doing my send after the fact. So in the ideal case, so let's just look at the first example. In the ideal case, my non-blocking is going to return right away, right? Because zero latency, infinite bandwidth. It's not going to take me any time to do the buffer copy from one MPI rank to another. Now, because my MPI receive has already been posted, that means that MPI receive is also going to, because the send message has already been posted, that means my MPI receive is going to return right away as well. But in the second case, I'm posting, if you just look at the first rank, my MPI non-blocking send is not going to take any time at all. But at that point, I have already posted my receive. So that means that any idle time I spend waiting for this is only going to be reduced by the amount of time I spend awaiting on my send to be posted. So some people generally recommend to post your sends, to do non-blocking sends, and to post your sends early. And this is sort of the reason why, right? Because in the first case, you will take advantage of a faster interconnect when that becomes available. Or you can do some optimizations within the MPI layer in order to make the MPI calls faster. But in the second case, you're never going to get rid of that latency at the beginning, unless you do more work in P2 in order to post your receive a little bit later. Now, what do we do with this data? So you can just take a look at, you can get the ideal trace file and then do a manual comparison between that one and the real one and so forth. But what we do with that data is we actually take a look at it, and then we try and do some sort of automatic sort of analysis. So there's something called the application imbalance diagram that's also available through the advanced menu from the GUI. So what that'll do is it'll automatically compare the real and the ideal trace files. And so it'll give you this sort of bar that's split into 3 segments. So the top segment is how much potential time or overhead you have that's rooted in the MPI, the physical MPI library. So that means if you improve the performance of the library or if you improve the performance of your interconnect, then that bar could potentially, or that segment of the bar could potentially shrink. The second section there is potential imbalance, or what percentage of your total runtime is actual imbalance. So that's when you're posting that receive early in my example previously. So in that case, it really is, so you're forcing some of your ranks to do this idling in the application. So what you really need to do is take a look at your application and figure out if there's some reordering or rearranging you can do. And the last section of the bar is just a pure calculations, nothing that's MPI related. So the only way you can really fix this is or reduce sort of the calculation phase is by changing some of the algorithms you're using, I suppose, or maybe apply multi-threading, things like that.
I noticed that since you bundled the communication time with the idle time, a lot of people are really interested in the communication time itself to find out what's going on in communication, because that can be the real bottleneck many times in MPI.
Right, that's true. That's true. So we do have something. So in a couple of slides, I have something. We have a new tool that does sort of lightweight statistics. That introduces some information about the MPI overhead. We have considered it in the past. It's just not something that's implemented. And we have a feature request in for the trace collector team. So I'll tell them that there's more people interested in sort of taking a look at that overhead caused by MPI library versus idling time. Yeah. There's also, so this is new in the previous version, but there's also new, something called the MPI Performance Assistant. So what this will do, right, so if you look at just the imbalance diagram, so this will just tell you overall where, or how much time you could potentially save by making particular changes, right? So what this will do is it'll actually try and match up certain situations, certain scenarios that are very performance intensive or that cause performance lag in MPI applications today, and tries to give you advice about how to potentially fix them. So for example, so in this particular example, it's detected that you might potentially have something called wait at barrier. So a barrier is not an MPI barrier, it's just some sort of a synchronization point, right? And it seems like some processes are arriving at the synchronization point earlier than others, and so it causes some of this idling time. So doing a better job of sort of balancing the work between the ranks will help here. And you can see, there's a little bit of text, and there's some examples at the bottom that sort of tell you how to fix that. So the nice thing about this is if you click on each sort of potential issues it finds, it'll tell you what the impact is on your application. So for this one, it's 0.9%. So if you fix this, you might potentially get 1% of your runtime back, right, theoretically. But what you want to take a look at is what is this duration here, and is that significant enough for you to worry about? And you can get directly to the source code from here as well. So we added a new summary page. So that's brand new in I guess that's new in the previous version. But we have just a quick breakdown of how much of my total time is spent in MPI and how much is computation bound. The nice thing here is that sort of it tells you whether your application is MPI or computation bound. If it's MPI, then it gives you some ideas of some of the other what kind of analysis you can do. If it is computation or CPU bound, then it actually gives you an example of a command you can run. So I don't know if Gary mentioned this, but vtune does support running under MPI applications. So you could get vtune level analysis for each of your individual MPI ranks. So what this will do is it'll give you an example of an example command that you can run to enable vtune for that. And then, of course, since Intel MPI supports MPI 3, then the trace analysis and collector certainly supports MPI 3 as well. So this is just an example of doing a non-blocking all reduce. So this is the new, sort of a new feature in the latest version, which is 9.1. We have added this MPI Performance Snapshot, which takes a look at lightweight level statistics for your application, and then try and gives you that in sort of this nice overview format. So if we take a look at just the trace analyze and collector, right, versus the MPI Performance Snapshot. So what is the reason for us introducing this lightweight version in the first place? So if you, the scalability of the trace collector is really optimal up to about 4,000 ranks or so. I mean, at some point you're going to start hitting physical limitations of your system, how much memory you have available in order to do this analysis. Also, when you're looking at, so if you're tracing about 1,000 MPI ranks, then you're going to get 17 gigabytes worth of trace data if you just use the defaults, right? So you can do some filtering before the fact, but it's really a large amount of data because it's 1,000 MPI ranks, right? So you're going to be doing a lot of MPI communication. On the flip side, if you look at the MPI Performance Snapshot, it's really meant for applications that do anything between 1,000 to even 100,000 MPI cores. So we have tested it internally up to 37,000 MPI ranks. Now, if you're looking at, so if you're collecting, 1,000 data for 1,000 ranks, then the amount of data collected is actually less than 1 gigabyte. So it's pretty manageable. It also doesn't grow exponentially as the application runs because it really just gathers mostly statistical hardware counter information. Sort of the data, the amount of data is set at the beginning, and it just sort of overrides some of the values within text files. It doesn't provide as much. It doesn't provide as much information as, let's say, the trace ends and collector, so you can't really get down to the individual MPI calls. But if you're looking at an application that scales to 10,000 ranks, then that's probably not what you care about. What you really care about is looking at your entire overview and figuring out what the potential issues might be. It uses PAPI events, so if you have the performance API available on the machine, or if you have vTune, so the latest version, if you have vTune, you can actually use the vTune performance counters as well in order to get information from the CPU, the OS, and so forth. So here's some of the information it provides you, and you know what, I just realized I don't think I have an example of how to run it. So the way to run it is just, so similar with when you do MPI run dash trace. So for this one, you just have to do MPI run dash MPS, which is the MPI Performance Snapshot. So it's actually pretty easy. You load this dynamic library, and it starts collection right away. So this is the information it provides. So just total wall clock time for all of your processes, as well as min and max, and which rank is reporting which ranks are doing the min and max CPU times. So what's important here is not the really absolute values, right? So 31 seconds for rank 0 and 35 seconds for rank 7. What you're really looking at is there a big difference between the min and the max, right? What's the delta between these two extremes? It also gives you hardware counter information, so it gives you floating point instructions, or what percentage of your application is doing floating point, what percentage of your application is doing it has vectorized instructions, and how much memory accesses it has for the application. So this is all information we get from the hardware counter side, as well as a bunch of memory statistics, right? And then on the MPI, and this is also really good if you're doing hybrid as well. So if you do MPI and OpenMP, it gives you sort of the imbalance, potentially the imbalance for your MPI communication, and the potential imbalance for the OpenMP threads as well. Now, this is just an example of some of the raw data. What we've added is the ability to do this HTML, export this HTML report, which may or may not be helpful. I guess it's more helpful if you're if you're running a project and you want to do sort of a high-level screenshot of what your application is doing. Then you can, we provide the ability to create these HTML reports, which basically just gives you, breakdown of your MPI time, your computation time, your OpenMP time. But what it is nice here is it actually categorizes some of these. So let's say for MPI, it tells you that this value is average. So you probably don't want to, you can do some optimizations here, but that's not really where your hotspots are. Where your hotspots are is probably in maybe in the serial time, right? So you have some amount of serial time, and you probably want to reduce that overall. That was it. So we have another library. I think I'll just skim through these really quickly. But we do have another library that really focuses on MPI correctness checking. So it takes a look at your application. It takes a look at the communication patterns that you're doing. And for each individual communication, it actually figures out if you're sending the right argument sets, if you're using the right data types, are there any potential data locks or data locks within your MPI application. So this is much So it has much more overhead than just running the trace lines on collector, right? So the collector is really meant to be profiling your application, and then you do the analysis after the fact. So this gives you real-time data as the application is running. But what it does is it sets up, so if you have, let's say, 2 MPI ranks here as an example, and you're running your MPI communication over some fast interconnect. What it actually does is it sets up its own internal secondary controls network, and it's running over just regular sockets, right? So if there are any optimizations on the fast network that might be causing corruption of your messages, it'll catch those. So what it does is intercepts all the MPI calls, and then for each one, it does a whole bunch of checks, right? So is the message that was sent the same message that was received? It does that both for point-to-point and global communication. Are there, I think I have a list. Yeah. Are there any corrupted messages? So one other thing that I think is kind of cool is if, let's say, you're overriding a buffer that hasn't yet been read, then you could potentially be losing that piece of information. It could be reading garbage information. So this tool will sort of warn you if you have any sort of memory overlap happening in your application. And I think that's it. So the way to run it is just say -check_MPI, and then it'll load up. So it's just, again, it's just another library. So you can just, you can load that up at runtime. And it'll start printing out information immediately. It just prints stuff out to standard error. But you can also create a trace file. So if you just enable this environment variable, VT-check tracing, if you just set that to on, it'll create a trace file in addition to doing this, this message checking output. Into the trace file, add these circles. And each circle, let's say a gray would be, a warning that it finds, and a black would be an error that it finds. So error could potentially be fatal to your application execution. It might be causing a crash. You might be getting a wrong result, things like that. And then you can right-click and get just more information on each individual issue. I don't know if you use any debuggers, but so this is not really meant to replace debuggers. It actually integrates really nicely with a lot of the parallel debuggers out there. So you can actually set a breakpoint in message checking breakpoint routine, and in that case, whenever it hits, so whenever the tool hits a potential issue, it'll just bring up the debugger automatically. In that case, you get access to things like your full call stack. You can get more information about whatever routine you're looking at, stuff like that. Okay. And that was actually, I guess I just have one slide on the benchmarks. So these are just a set of kernel tests that we run to do performance, mostly just to gauge the performance of both the MPI implementation. So I showed you the performance slides at the beginning. We ran these particular benchmarks, but also to check the performance of your cluster. So it gives you both latency and bandwidth benchmarks. So it's kind of nice to figure out if, let's say, Mellanox is telling you you're supposed to be getting certain bandwidth, but you're not really getting that. I think that's it. We have a lot of online resources. We create a lot of online articles. We have pretty active forums for the tools as well. And so it's people like me, support engineers. It's people like developers from the MPI and the trace collector team. So they sort of look at the forums. So if you have any issues, you're welcome to post on there as well. So yeah, I think that's it. Any questions? Cool. Is this helpful? It's okay. Okay. Well, I'll be here, I guess 3:05 for another few minutes. So if you guys want to chat, or if anyone wants to actually try this out on their code, we can definitely do that. It seems like the tools are available on the cluster today. So.
And we also have these here. Does everybody sign the sign-in sheet?